Okay, now let's discuss the third practice exam. So first, we have fx equal to square root of x. We have g of x equal to 2x minus 1. And we have h of x equal to x squared. Question A, find f composed with g evaluated at 5. Okay, so this expression f circle g of 5 is f of g of 5. G of 5, g of x is 2x minus 1. G of 5 will be 2 times 5, 10, minus 1, 9. So it is f 9. So it's a 2 times 5 minus 1 is 9. F9 is the square root of 9 is equal to 3. So the answer is 3. Part B, it is h composed with g composed with f of 9. So it is h of g of f of 9. F of 9, f is square root of x. It's a square root of 9. Square root of 9 is a 3. So it's a h of g of 3. G of 3 is a 2 times 3, 6, minus 1, 5. So h of 5. H of 5, h of x is x squared. H of 5 is 5 squared, 25. Okay, that's problem 1. Problem 2, we have fx equal to 1 over x plus 2. Gx equal to 4 over x minus 1. Find the composite function and the domain. A, f composed with g. We're looking for the expression, formula of f composed with g. So it's f of g of x. G of x, 4 over x minus 1. So it's f of 4 over x minus 1. You do substitution here. You see, you have the denominator x minus 1. So this place, it requires x minus 1 is not equal to 0. So whenever you have a ratio, the denominator is not equal to 0. That's one condition. And then you apply the f function. F of x is 1 over input plus 2. So it is 1 over input plus 2. See, you see here, you have the second ratio. Whenever you have a second ratio, you require this second ratio is not equal to 0. So the formula, you can leave the formula like this, 1 over 4 over x minus 1 plus 2. Don't simplify it, okay? But you have to figure out what is the corresponding value here. This one, x minus 1 is not equal to 0. So x is not equal to 1. That's one requirement, limit. And this one, you're going to solve for x. For example, let's solve for it here. We let it equal to 0 and move 2 to the right side. Multiply two sides by x minus 1. So it's 4 is equal to negative 2x and plus 2. Subtract 2 from two sides. So x is negative 1. Which means when x is negative 1, this expression is equal to 0, but we do not allow it to be 0. So x is not equal to negative 1. All right, so the domain is the set of all real numbers except negative 1 and positive 1. So it's a negative infinity to negative 1, negative 1 to 1, 1 to infinity. All right, that's for part A. Part B is similar. So we're looking for f compose f of x. G compose f. G compose f of x. Different order. So it's a g of f of x. G of f of x. fx, 1 over x plus 2. So it's equal to g of 1 over x plus 2. You see you have ratio. Ratio implies the denominator is not equal to 0. So x plus 2 is not equal to 0 here. And then you continue this substitution. So g of x is 4 over input minus 1. So here it is 4 over input. This expression is input. And then minus 1. Okay, so this is a formula for the g composed f of x. Don't simplify it in the exam. But whenever you see here, you have the second ratio. Second ratio means 1 over x plus 2 and minus 1 is not equal to 0. So similar. It's very similar to the first one. You have to figure out what is the solution. So let's do it here. So 1 over x plus 2 minus 1 is equal to 0. Move 1 to the right side. 1 over x plus 2 is equal to 1. Two sides, multiply two sides by x plus 2 is 1 is equal to x plus 2. So x is negative 1. When x is negative 1, this denominator becomes 0. So we want to exclude that case. So x cannot be negative 1. Here, x is not equal to negative 2. So this is one bad point. This is another bad point. This negative 2 will make this denominator equal to 0. Here, negative 1 will make this bigger denominator equal to 0. So both cases cannot happen. So the domain is the set of all the real numbers except the negative 1 and the negative 2. Alright, except negative 1 and the negative 2. So we exclude negative 1 and negative 2 from the number line. Okay, so this is second problem, part B. Problem 1, AB, and problem 2, AB. Okay, let's see the problem 3. Problem 3, a function is given fx is equal to square root of x plus 2 and minus 3. Find the inverse of this given function. To find the inverse of a given function, first we let y be fx. So y is equal to this expression. And second, we interchange x and y. Interchange x and y. And then we solve y in terms of x. We're looking for y equal to something of x. So we move 3 to the left side. X plus 3 is equal to square root of y plus 2. And then we square two sides. X plus 3 squared is equal to y plus 2. You square the right hand side, you cancel the square root. And move 2 to the left side. So x plus 3 squared minus 2 is equal to y. So the inverse function f inverse of x is equal to x plus 3 squared and minus 2, this side. Because f inverse is this one. Right? So the problem does not ask you to find the domain, so you don't need to look for the domain. Okay. Problem 4. Problem 4, there is a function given by the pairs of given by the collection of ordered pairs. So negative 1, 5, 0, 0, and 2, 6. This expression just means f will map negative 1 to 5, 0 to 0, 2 to 6. That's what it means. Then we are looking for f inverse. F inverse, just interchange x and y. That's the first step we did here. Interchange x and y. So you will have 5, negative 1, 0, 0, but yeah, and 6, 2. This is inverse. Inverse just interchange input and output. And then you're looking for f inverse of 5. F inverse of 5, see here, it will map 5 to negative 1. So f inverse of 5 is negative 1. And then f inverse compose with f of 2. Check here, f2. f2 is 6. f map 2 to 6. So f2 is, this inside is a 6. So f inverse of 6. And f inverse maps 6 to 2. Right? So this is like the verification that f inverse composed with f is identity map. It maps 2 to itself. 1, 2 is in the domain of F. Okay. Problem 5. Problem 5, we are given a quadratic function negative 2x squared minus 4x plus 3. Find the vertex and the symmetric axis. Vertex is negative b over 2a. 4ac minus b squared over what? Over 4a. Right? And then the symmetric axis is x equal to negative b over 2a. Symmetric axis, negative x is equal to negative b over 2a. Be careful, this is a line, so it is x equal to it. It's not just a single number. So a, b, c, a is negative 2, and b is negative 4, and c is 3. So let's compute. Vertex is negative b over 2a. 2 times a is negative 4. 4ac minus b squared over 4a. Okay, so negative 4 over negative 4 is 1, so it's negative 1. Here, 4 times negative 2 is negative 8 times 3, negative 24, minus negative 4 squared is 16, over 4 times negative 2, negative 8. Keep computation. Negative 24 minus 16 is negative 40. Negative 40 over negative 8 is 5. So the vertex is negative 1 and 5. The symmetric axis is x equal to, symmetric axis is actually x equal to the first coordinate, x coordinate of vertex, x equal to negative 1. X is equal to the negative 1. Okay, so that is a vertex and symmetric axis. Okay, problem 6. Form a polynomial function whose real zeros and degrees are given. So we want 0, 1. 1 is a 0. Multiplicity is 1. All right? So no, not 1. Negative 1 is 0. Multiplicity is 1. 3 is a 0. Multiplicity is 2. And the degree is 3. So if we read it, it's like this. Okay, whenever you have negative 1 as 0, it means it has a factor. The polynomial function will have a factor x minus negative 1. The multiplicity is 1, so the power is 1. The 0 is 3, so the factor is x minus 3. Multiplicity is 2, so the power is 2. If you can count the degree of this polynomial, it's 1 plus 2 is 3. So this function will satisfy all the required conditions, which is x plus 1, x minus 3 squared. We only need to construct one polynomial function. This one satisfies the condition, that's it. All right, 7. 7, we have a rational function, 2x squared plus 3x and minus 5 over x plus 2. We're looking for all possible asymptotes. To find asymptotes, first I want to see if it is in the lowest term or not. So I'm going to factor the numerator. To factor the numerator, you see 2, negative 5, the product is negative 10. Then I need to factor negative 10 as a product of two numbers so that the sum of them is a 3. So I see it's a 5, negative 2. 5, negative 2. 5 plus negative 2 is a 3. So 5 means I will have 5x. Negative 2 means I will have negative 2x. 5x plus negative 2x is this a 3x. So 2x squared and plus 5x and minus 3x and minus 5. Okay, and then we factor out x from the first two terms, x times 2x plus 5. And the last two terms we factor out a negative sign. 2x, that's my bad, not 3x, 2x. Here's 2. 2x. Factor out the negative sign is 2x minus 5. Plus 5, my bad. X plus 2. So you have 2x plus 5, 2x plus 5. You continue the factorization, 2x plus 5. Then this is x minus 1 and x plus 2. So you see there's no cancellation. This rational function is in the lowest term. All right, now let's count. First of all, this one, the numerator has degree 2, denominator has degree 1. The difference of degrees is 1, so it has a slant asymptote. It does not have horizontal asymptote. It only has slant asymptote. Okay, to compute the slant asymptote, we do the long division. We divide the leading term by leading term. So 2x squared over x is 2x. So we put the 2x above 3x. We multiply all the terms from the denominator with 2x. It's 2x squared plus 4x. And then you use row 1 to subtract the row 2. 2x squared, they cancel. 3x minus 4x is negative x. And you move this negative 5 down. And the negative x is leading term over x is negative 1. So you write a negative 1 here above 5. And then negative 1 times x, negative 1 times 2. And negative x minus negative x cancelled. Negative 5 minus negative 2 is negative 3. Negative 5 minus negative 2 is negative 5 plus 2 is negative 3. So that's here. And the slant asymptote will be this point, will be this line. Y equal to 2x minus 1 is the slant asymptote. Okay, y equal to 2x minus 1 is slant asymptote. All right, so that's a slant asymptote. And here, remember, we already did the factorization. We noticed that this is in the lowest term. For the lowest term, all the zeros from the denominator will give us vertex asymptote. So you just let x plus 2 equal to 0. You get x equal to negative 2, and this is the vertical asymptote. Okay, x equal to negative 2 is vertical asymptote. This is correct only when you have rational function in lowest terms. You have to cancel all the duplicate terms from top and the bottom. Okay, so that's our problem 7. And then let's do problem 8. Problem 8, we are going to use mathematical induction to prove this statement. It says 1 plus 2 plus 3 plus up to n is always n plus 1 over 2. So to apply mathematical induction, we have fixed 3 steps. First, this is true for all positive n. For all positive n. So all positive n starts from 1. So 1, n is equal to 1. N is equal to 1. If you want to prove this is equality, you cannot first assume it. You have to always say left hand side is 1. You only have 1 because it's like a sum of first n integers. N is 1, just the first one. Okay, left hand side is 1, and right hand side is 1 times 1 plus 1 is 2 and over 2. 1 times 2 is 2, over 2 is 1. So you see, you separately compute left hand side is 1. You separately compute right hand side is also 1. So the left hand side is equal to the right hand side. The statement is checked. Okay, that's the first step. We always check the first step. And second, we will say assume for n equal to k, we know the statement is correct. The statement is correct. Okay, you must mention this. Assume that for n equal to k, the statement is correct. And then we'll go to next step. Now before we do that, the statement is correct means if you add from 1, 2, 3 up to k, it should be equal to k times k plus 1 over 2. Remember, we only say up to this k. This is correct. What happened about the k plus 1? So far we don't know. We just know we already verified the first few terms. All right? The first few possibilities. Only when this k, this n stops at k, that it is equal to k times k plus 1 over 2. That's what we assume. And now, with this in mind, we're going to say, now we check the next number. Now let n be k plus 1, the next one. We explore the new world. Next one, true or false, we don't know. We start from left hand side, which is 1 plus 2 plus 3 plus up to k, and then k plus 1. Remember, the left hand side is just the sum of first n integers, n positive integers. So you start from 1, 2, 3. The last one will be k plus 1. The first 10 positive integers, last one will be 10. First 100 positive integers, sum of positive integers, last one is 100. So first k plus 1 positive integers, last one is k plus 1. Then the one before it will be k. The one before 10 is 9. The one before 100 is 99. So the one before k plus 1 is k. This is a left hand side. But we notice that here, this partial sum, not the total one, this appears in the previous statement. And we assume we already know what it is. It's a k plus 1 over 2. So the left hand side, by the assumption, the partial sum is k plus 1 over 2, and then plus k plus 1. Okay, this number is not in the sum from the previous one. All right, and now we're going to simplify. You see here, k plus 1, k plus 1. We factor out k plus 1. And then this part becomes k over 2 and plus 1. K over 2 plus 1 is, you see, it's 2 and k plus 2. Because 1, it becomes 2 over 2. This 1 is a 2 over 2. And then they have the same denominator. It's a k plus 2 over 2. So it's like this, right? So this is a one factor. This factor times this sum. This sum is written as a ratio, and you write this together with a numerator. That's left hand side. Left hand side can be simplified to this form based on the assumption. And then the right hand side. The right hand side, remember, right hand side is n plus 1 over 2. That's the right hand side. Now n is a k plus 1, so it's a k plus 1. And then n plus 1, it will be k plus 1 plus 1. K plus 1 plus 1 over 2. That's the right hand side. And we simplify it. K plus 1 plus 1 is a k plus 2 over 2. You see, left hand side is equal to this expression. Right hand side is also is equal to this expression. So left hand side is equal to the right hand side. We finish those 3 steps, we will say by mathematical induction. the statement is true for all positive integer n. Okay, so for all positive integer n, this is the required steps for mathematical induction. Okay. Problem 9. Problem 9 is has a very fixed step. So the exercise here, I put a lot of part, but in the real problem, it might not be such complex. So remember, for whatever function y is equal to fx, here it says we are going to shift the graph vertically up. Whenever you shift up 2 units, if you shift up 2 units, then the function becomes fx plus 2. Y is equal to fx plus 2. Okay? I will use fx, and eventually I will replace fx by the given function. Go up 2 units. Go down, it becomes minus. Okay? Up is plus. Down is a minus. Horizontally left 3 units. Horizontally left 3 units. Whenever you see this to the left, it is x plus 3. So it's a y equal to f of x plus 3. And plus 2, because I already finished this step, so plus 2 I copy it. It's like a chain of operations. Shift to the left plus the unit. Shift to the right minus the unit. Okay? And next, stretching vertically by factor 4. If you stretch vertically by factor 4, be careful. Now this is your current function. Stretching it vertically means you're going to multiply the whole function by 4. Whole function, whatever function you have from the previous step, you always put parentheses and times 4. Okay, that's a vertical stretching. And horizontal compression by 5. Horizontal compression by 5 means whenever you have the x, whenever you have this whole thing is x. Right? Let's see. So far, let's see what it is. Let's see what it is. This is x squared plus x and minus 1. It's x squared plus x minus 1. Now let's try to, before I do this compression, horizontal compression by 5, let's try to compute it. So fx plus 3. Fx plus 3. So input becomes x plus 3. So it's x plus 3 squared plus x plus 3 and minus 1. This is fx plus 3. And then plus 2. And then plus 2. And it is 4 times x plus 3 squared and plus x plus 3 and plus 1. Minus 1 plus 2 is a plus 1. Okay, so that's this quantity. And let's have this. Okay, so now you see x is still the input. Input is still just x. Input is x. For example, we are not going to use f to represent the expression. We're going to use g to represent the expression. And okay, so far we get vertical stretching. We have such stuff. And then we're going to apply the horizontal compression by 5. Horizontal compression means you're going to multiply x by 5. So it's y equal to g of 5x. Y equal to g of 5x. You always handle x is horizontal. Okay, so whenever you have x, you're going to write 5x. So it becomes 4 big parentheses, 5x becomes 5x and plus 3 squared and plus 5x plus 3 and plus 1. Sorry, here, this one. Okay, because let me copy it here. Gx is this.